In Chapter 3, we are going to compare the sizes of infinite sets. First of all, let's recall what infinite sets have you met. Well, after we finished with Chapter 2, you know that we had the set of real numbers, all decimal numbers, and they were made up of two mutually exclusive sets of numbers, the rationals, I'll just call it the rats, and let's say IRR for the irrats. We have the rationals and the irrationals, certainly infinite sets. And a subset of the rationals would be the integers, and a subset of the integers were the natural numbers. And we had several infinite sets that we could say are subsets of the natural numbers. We had the Fibonacci numbers, we have the prime numbers, we had the even numbers, we have the odd numbers, and there are infinitely many ways you could make up infinite subsets of the natural numbers. So these are all infinite sets. Now, we are going to, in Chapter 3, we are going to take the one we are most familiar with, the natural numbers, and we are going to compare all other infinite sets to capital N. We're going to ask ourselves, is the set of prime numbers smaller than N? Is the set of even numbers smaller than N? Or are the integers a larger size of infinity? Are the rational numbers larger than N? Well, this is going to be hard to do. This is something you've never thought of. If we want to compare two finite sets, finite set is just a set that we're all very familiar with. A finite set has a certain number of elements in it. If I wanted to compare the size of the set of fingers on my left hand and the set of vowels in the English language, I could just count them. 1, 2, 3, 4, 5 fingers, 1, 2, 3, 4, 5 vowels. So they're both size 5, and they are the same size. So it's easy to compare finite sets. You can just count. If they're not too big, you could just count the elements in one, count the elements in the other, and see if they're the same size. But we can't count in infinite sets. We'd never get done, would we? So we have to figure another way of comparing the sizes of sets without counting. Two collections or two sets of objects are equally numerous, in other words, the same size, if there exists a one-to-one correspondence between the elements of the two sets. We say the two sets have the same cardinality. So let me give you an example of comparing two sets without counting. Let's say you have an 18-month-old baby. Now that baby cannot count, but he sure knows who's in his family. So he has a mom, a dad, and himself. Right? Those are the members of his family. And one night he comes out and he sees these plates on the table, and he asks his mom if, who's coming for dinner? Is Grandma coming? Well, how did he know? He can't count to 3 members of his family, and he can't count to 4. He has no concept of number. So what did he do? Well, he made a one-to-one. He tried to make a correspondence between his mom, his dad, and his plate. And he sees an extra plate. In other words, he's used to corresponding his family to the plates on the table, but this time he cannot make a one-to-one correspondence. There is an extra plate. And so This is the very simplest way of comparing two sizes of sets. So simple that an 18-month-old can do it. And I'd like you to kind of forget about what you know and think deeply about this concept. Two sets, whether they're finite or infinite, two sets have the same cardinality. It just means they're the same size. In the case of finite sets, it means they have the same number of elements. But in general, it means there is a way to make a one-to-one correspondence between the elements of the two sets. This is an example from the text of trying to see clearly what we mean by comparing two sets by seeing if there is a one-to-one correspondence, not with counting, just that very simple thing that the baby did. Suppose we have a huge barrel full of Volvos. Obviously this is in the author's imagination. And a barrel full of soccer balls. And we want to know if there are more Volvos than soccer balls, or more soccer balls than Volvos, or is there the same number of each? Do the two barrels have the same cardinality of elements? How could we decide? We want to devise a method for comparing the barrels without counting the Volvos or soccer balls. Well, we could take one Volvo from the first barrel and one soccer ball from the second and pair them up. We could put the ball in the trunk and go on and take out another Volvo from the first barrel and a soccer ball from the second, put it in the trunk. And if we continue pairing in this fashion, we could tell whether we have the same number of Volvos and soccer balls without ever knowing how many we actually have. How can we tell if another infinite set has the same size as n, the same cardinality as n? Well, first we can just use the definition that we had. We can say an infinite set S, let's give it a name, an infinite set S has the same cardinality. I'll put card all throughout the lecture. The same cardinality as capital N if there is a way to set up a one-to-one correspondence between S, the elements of S, and N, the elements of N. Can we set up a one-to-one correspondence? If we can show that there is one, the two sets have the same cardinality. They are the same size. And by the way, the natural numbers does have a cardinality. Of course, it's not a number because it's an infinite set. And it is called, let me write, the cardinality. This isn't in the book, but it's nice to have a name for it. The cardinality of the natural numbers is, it's called Aleph, A-L-E-P-H, Aleph naught, N-A-U-G-H-T, Aleph naught. Sometimes it's called Aleph zero or Aleph null. But this is what it looks like. It's a Hebrew character. That looks better. This is Aleph naught. It's the cardinality of the natural numbers. And if another set has cardinality Aleph naught, we can prove that by showing that there is a one-to-one correspondence between that set and the set of natural numbers. We're going to start by looking at infinite sets which we may perceive or expect to be smaller than capital N. We may think that they would have a smaller cardinality if we go by our intuition that we have for finite sets. Let's start with the natural numbers, and if we take out the first 5 numbers in the set, then have we made the remaining set smaller? Well, what is the remaining set? Let's write S. No, I won't give it a name. I'll just say remaining set. Whoops. Remaining set is, okay, we throw out the first 5, so it will be 6, 7, 8, 9, 10, ... That's the remaining set. I left off the set brackets there. Is there a one-to-one correspondence? It seems like it would be smaller, doesn't it? Seems like it would be smaller because we threw out some numbers. Certainly in a finite set, if we have the set of 25 numbers and we throw out 5 of them, we're going to be left with a set with 20 numbers, a smaller set. But can we make a one-to-one correspondence between this remaining set and the natural numbers? Well, let's see. I'm going to put 1, 2, just little numbers here. And you see, there's a real easy way to set up a one-to-one correspondence. This remaining set was just written as a list. It had a first, a second, a third, a fourth, a fifth, and we would just assign the natural number, the number to its position number on the list. In other words, we'll correspond 1 to 6, 2 to 7, 3 to 8, 4 to 5, 4 to 9, 5 to 10. And can you see that all natural numbers will be paired with a number in the remaining set, and every number in the remaining set will be paired with a natural number. There's actually a formula for this. N in the natural numbers is corresponding to, well, it's n plus 5, right? Now, you don't need to know formulas for the correspondence, but this one's pretty obvious. The natural number corresponds to n plus 5. This is a one-to-one correspondence. Therefore, the cardinality of the remaining set is equal to the cardinality of n, even though we threw out some elements. Well, how about if we throw out more elements? Let's throw out all the even numbers. Well, what's left? Well, obviously it would be the odd numbers. I'll call it O, capital O. This is what's left. It's the odd numbers. So we'll start with 1, 3. I want to list them out. 1, 3, 5, 7, 9, and so on. That's what we're left with. Now, it seems to our intuition like we've thrown out half of the set of natural numbers. Certainly the remaining set would be smaller, wouldn't it? A smaller size? Well, the way that we compare to n is simply one thing. Is there a one-to-one correspondence? So, let's see. O can be listed out this way, so I could do the same trick. I'll just assign the first number to 1, the second on the list to 2, the third on the list 4 to the fourth on the list, and 5 to the fifth on the list, etc. Now, can you see that every natural number in yellow will be associated with an odd number? 6 will be associated with 11, and 7 will be associated with 13, etc. And every single odd number will be associated to will be paired with a natural number. Let's take the number 23, for example. Can you guess what it would be? Not guess. Can you figure out what it would be paired with in the natural number? Look at these. If we add 1 to 3 and divide by 2, add 1 to 5 and divide by 2, add 1 to 7, we get 8, divide by 2. So this will be, if we add 1 to 23, we get 24, and we will get the number 12. Every odd number has a natural number paired with it. Therefore, the cardinality, let's write this out. The cardinality of the odd numbers is equal to the cardinality of the natural numbers, which is Aleph naught. So in that last example, we threw out infinitely many. We threw out all the evens, and yet we didn't make the remaining set any smaller in size. Well, let's see. Does that always happen? What if we toss out all numbers greater than 1,000? Then what do we have left? Well, let's just call it L for left. What we have left is the set of numbers 1, 2, 3, 4, and so on, up to and including greater than 1,000. Okay, so I'll put that in, and then the last one is 1,000. We threw out all the numbers bigger. So it's all numbers between 1 and 1,000. Notice the ... there just means and so on. I don't want to list 1,000 numbers on this video. So I establish a pattern, I write ... and give you the last one or two. And you know what L is. Well, what is the cardinality of L? That's a finite set. It has 1,000 elements, 1,000 numbers in it. So its cardinality is 1,000. And that certainly is not the cardinality of n. It is a finite cardinality. It is less than Aleph naught. There is no finite set that has the same cardinality as n. So here we threw out an infinite set, and we were left with a smaller set. So what we've seen in the case of the natural numbers, an infinite set, that we can throw out some and not even change the size of the set. We could throw out infinitely many and not change the size of the remaining set. Or, in this case, we threw out infinitely many and we were left with a finite set. Well, this should seem strange to you because all of our intuition is built upon finite sets. And what happens if you remove elements from a finite set? Well, the remaining set has a smaller cardinality. Or for finite sets, you could say the remaining set has fewer elements. If you throw some out, the set gets smaller. This is what our intuition tells us would happen with infinite sets, but once we see how we compare infinite sets, we see that it is not always true. Now, as we have noticed in the few examples we did, if you could make a list of the infinite set in question, it always turns out that if you can list the set, then the one-to-one correspondence is established between the natural numbers, because the first number on the list corresponds to its position on the list. The second number on the list corresponds to 2, its position on the list. The nth number on the list corresponds to its position on the list, n. And so listing is a method of showing that, or of proving that an infinite set has the same cardinality as n. Now I'd like to read, we've said this once, but it is the essence of all of Chapter 3. If you guys get this down now, the rest of Chapter 3 is going to make sense to you. A one-to-one correspondence between an infinite set S and the natural numbers n is a pairing of elements so that each element of S is paired with exactly one natural number, and each natural number is paired with exactly one element of S. And you can show this by just finding a method of listing the elements of the infinite set in question. Let's say that we take the even numbers, all the even natural numbers. Well, I'll put 2 as first on the list, 4, 6, 8, 10, and so on. Now, in this case, I actually know a formula because obviously n is paired with 2n. 5 is 2 times 5. So that even number that will be there will be 2n. And this one would be 2 times n plus 1. But again, we are not so concerned with you coming up with a formula. We want you to just show how you could list the set and be sure that every number was on the list, each only one. Well, we have looked at infinite subsets of the natural numbers, like the evens, the odds, the Fibonacci's, the primes, and we've seen that they have the same cardinality as n. They are not smaller sets. Well, let's see if we could find a set bigger than the natural numbers. What do we mean by that? A larger cardinality than n. In other words, it would be impossible, we would have to show it impossible to find a one-to-one correspondence between that set and n. The best way to think of it is we're looking for a set that's too big to fit on an infinite list. Let's take as our first example the set of integers. Notice the set of natural numbers, they're right here. The set of natural numbers is a subset of the integers, but the integers include much more, 0 and all the negative numbers. So it looks like I might be bigger than n. It certainly contains many numbers that n does not, but is the cardinality of I bigger than the cardinality of n? Our question is, can we fit all of the integers, each only once, on an infinite list? So let me draw out what we're asking here. Can we put a first one on, and a second one, and a third one, and a fourth one, and a fifth one, and keep going forever, guaranteeing by the method by which we create the list that every integer will be on that list, each only once? Well, the way that I gave you the set here is not a list, because it goes infinitely in the left direction, in the negative direction, and infinitely in the positive. It has two sets of dot, dot, dots. So this is not in the form of a list, because there isn't a first, a second, a third. But could we put it into a different form where we get all of them? And the answer is yes. You would be really smart to put this on pause right now and see if there's any way that you could figure out a way to put a first one down. I'll give you a hint. Make 0 the first one. And now, how could we get all the negative and positive integers onto this list? Well, I hope you put it on pause, and here's one way to do it. It's not the only way. 0, how about 1 minus 1, 2 minus 2, 3 minus 3, and so on. There's a list. We can see it is indeed an infinite list. The numbers on that list are in one-to-one correspondence with the natural numbers. Each number on the list corresponds to its position on the list. And yes, all of the integers are on the list. So we can say that the cardinality of I is equal to the cardinality of n. The integers are not a bigger size of infinity. Now the little question down below is, in this correspondence that I set up, what integer corresponds to the natural number 10? Well, the answer will be, I have to look for it, it'll be the 10th on list. So I have to go out 10. This is 5, 6, 7, and then I'll have 4 minus 4, and 5 minus 5. Let's see, this was the 5th, 6th, 7th, 8th, 9th, 10th. There we are, 5. The integer 5 is the 10th on the list, so in this particular one-to-one correspondence, the natural number 10 corresponds to the integer 5. Now that list that I just made is not the only way to list the integers. Let me give you another way. How about 0, minus 1, minus 2, and then I'll put 1, 2, and then minus 3, minus 4, and then 3, 4, and then what's next? Well, it would be minus 5, minus 6, 5, 6, and so on. That's kind of a more complicated list, but they're all there. You can see a method by which I did the listing, and they are all on the list, each only once. So let's answer the question, what integer now on this list corresponds to the natural number 10? We just count over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, 5 is the 10th integer on the list. So that means that the natural number 10 corresponds to the integer minus 5 in this particular list. There's not just one way of making a list, but all you need is the existence of one way in order to conclude that the cardinality of I is equal to the cardinality of n. Here's a list of integers. Well, that doesn't include all of them, does it? This is a correspondence between integers and natural numbers, but it fails to be one-to-one because there are integers which are not on the list. Okay, that's easy to see, but here's the question. What if you did do that first and you saw, oh, there's a correspondence, it doesn't work? Could you say, oh, well, therefore, they don't have the same cardinality? No. The failure of this list to create a one-to-one correspondence does not mean that the sets have different cardinalities. It just means that this correspondence is not one-to-one. Remember, two sets have the same cardinality if there exists a way to make a one-to-one correspondence. There just has to exist one. Many correspondences fail to be one-to-one. So what we have learned is that infinite sets that can be put on a list have the same cardinality as n. So in our search for an infinite set that is bigger or has a larger cardinality than n, basically what we're trying to do is find a set of numbers that is too big to fit on a list.